Where's my whiteboard? Here's my whiteboard. Section 4.6. Oops. Yes, I know that. Thank you. There we go. Again, I can't see all of you, so virtual hand raises at this point in time, please. Goodness, not doing well. Okay, section 4.6. Impulses and delta functions. Impulses and delta functions, and we're spending today and tomorrow on section 4.6. So we're not going to get all the way through the section today. I am okay with that. Impulses and delta functions. So here's an impulse function. Imagine we've been doing differential equations for a while, right? And one of our practical applications is an object moving back and forth on a spring, right? We talked about this application, and we talked about sometimes there is free motion, which means there's no external force acting on the object. And sometimes there's forced motion and there is an external force acting on the object. So we've got those two different types of motions. Those should hopefully sound familiar back from chapter 2. An impulse function is basically an instantaneous force acting on an object. So an impulse function is an instantaneous force acting on an object. If you have an object moving back and forth on a spring, what this means is you give it a shove at a certain point in time. And there's two things going on that we need to deal with: the time at which we gave the object a shove and the magnitude that we shoved it with. So two things going on, okay? The time at which we shoved it and the magnitude that we shoved it with, two things. So we have this impulse function, it's called the delta function. And it is going to be denoted by delta, that's a delta, a lowercase delta, sub A of t, okay? So this is a shove, or an impulse, but shove sounds more fun, of magnitude 1 at time t equals a. I have to tell you how this function is defined mathematically, but that's what this function is indicating. You're going to shove an object with magnitude 1, whatever 1 means in terms of the units you are using for your problem, and we're doing it at time t equals a. Sometimes we also do, and you should be familiar with this with the unit step function, delta of t minus a. So sometimes we use delta sub a of t, and sometimes we use delta of t minus a. Both of those mean the exact same thing. So then if we want, I'm doing a mathematical definition in just a sec, but we're talking conceptually first. If we want a shove of magnitude p at time t equals a, then what we need to use is p times delta sub a of t. So we have to multiply the function by whatever we want our magnitude to be. Our default magnitude is 1, and if we want a different magnitude, if we want to shove it harder or less hard, then you would have a fraction. Then you need to multiply by p out in front. So that's the concept of this function. We got to do a mathematical definition, but that's the concept. Concept of this function makes sense? Yes, basic concept, what's going on? Okay, so here's how this gets defined. Delta sub a of t is the function so that for any other function, g of t, we have this relationship. The integral from 0 to infinity of g of t times delta sub a of t dt is equal to g of a. So the integral from 0 to infinity of g of t delta sub a of t dt is equal to g of a. What's going on is I want to get the value of the function that I am working with, g of t, when the impulse happened, and then I want zeros everywhere else. So that's the definition of this function. We're not going to use the definition of this function very often, but we need the definition of this function to get its Laplace transform, because this is a function that's a force, and so therefore it can show up on the right-hand side of a differential equation, right? Think about the equations that model object moving back and forth. The external force is always on the right-hand side, so this function can show up on the right-hand side of a differential equation. And if this function shows up on the right-hand side of a differential equation and we want to solve that differential equation using Laplace transforms, we got to know how to take the Laplace transform of this function. You could cheat by looking in the front of your book, but we're going to come up with what it is because it isn't actually that hard to do. So what's the Laplace transform of the delta function? Because then we can use this in differential equations to solve them. Definition, go back to the definition. Integral from 0 to infinity, delta sub a of t, e to the negative st dt, right? Way back to the definition, the one you don't like, justifiably so, because it's a yucky integral and it's hard to do and it's not particularly enjoyable, but that's going to be our Laplace transform. Okay, so now I should have done this on the same slide. I didn't, sorry. Think of this e to the negative st as g of t. So in my previous slide, right, we had this delta function that has the property, these two are backwards, but that's okay. So if I have an integral with this delta function times some other function, I evaluate that some other function at a. What I've got here is an integral with this delta function times some other function. So I evaluate that some other function at a. So it's e to the negative s times a, or usually we write it as e to the negative a times s. We usually reverse the two letters. This is the important part from today. Okay, and that is also in the front of your book, but now we know why. So it's in the front of your book. Where is it? Second column, third from the bottom. So it's in the front of your book, second column, third from the bottom, if you want to find it there. But I've demonstrated why it actually works. Okay, I am going to pause and stop sharing my screen and see if there are questions before we do an example. So anybody for questions at this point in time? Anything for questions before we try an example with an impulse function on the right-hand side and try to solve a differential equation? Anybody, anything at this point in time? I think you probably need to see an example. Yeah? Okay, all right. So how about this one? For example, here's my differential equation. X double prime plus 4x equals 3 delta sub 0 of t. X naught is 0 and x naught prime is 0. X double prime plus 4x equals 3 delta sub 0 of t. X naught is 0 and x naught prime is 0, and we want to solve. So Laplace transforms. S squared, capital X of s, minus 0s minus 0. I'm going to stop writing those in just a second, but it's been a little while since we've done a differential equation, so it's good to put those back in. plus 4 capital X of S. That's the left-hand side. We're okay with the left-hand side? Left-hand side, we're good? All right, and then right-hand side, A is equal to 0 in this case, right? That's my delta function. A is equal to 0. So this is going to be 3e to the negative 0 times S. I won't write that out every single time, but I want to write it out this time for the first one so you can see where this is coming from. So A is equal to 0 in my delta function this time. And so therefore the transform, there's a 3 out in front, e to the negative 0 times S. Okay, we're good with this now. We know how to solve this. This right-hand side just goes to 3. So capital X of S is 3 over S squared plus 4. Capital X of S is 3 over S squared plus 4. Front of your book, please. Go ahead, front of your book, see what you get. See if you can do the inverse transform of this. What's this going to turn out to be? Inverse transform, what's my little x of t? You're going to have to mess with the coefficients in the numerator just a little bit. Should be looking at a sign. Should have a sign function. So we need a 2 in the numerator, which means we are going to have a 3 halves out in front. 3 halves sine of 2t. So if I have an object that is moving according to the left-hand side, and I shove it with a magnitude of 3 at time 0, my object is going to move according to this function. That makes sense because this is undamped motion, right? Think way back to chapter 2. The x prime coefficient is 0, so there's no damping going on here, and therefore I'm going to get perpetual motion according to a sine function because there's no damping going on whatsoever. Okay. All right, one note, and then we're going to do the next one. I should have mentioned this before, and I forgot. So a lot of times, delta sub 0 of t, if a is equal to 0, is just going to be written as delta of t. So a lot of times when a is equal to 0, we just leave the subscript off. Subscript off if a is equal to 0. All right, let's try one where a is not equal to 0. We're going to make it a little bit more interesting here. So how about this one? We've got x double prime plus 2x prime plus 2x equals 2 delta sub pi of t. And once again, x naught is 0 and x naught prime is 0. X double prime plus 2x prime plus 2x equals 2 delta sub pi of t, x naught is 0 and x naught prime is 0. One more time, analyzing the motion that we have. So first of all, x naught is 0, which means the object starts at equilibrium. It's not stretched or compressed, the object starts at equilibrium. X naught prime is 0, so the object starts with no initial velocity whatsoever, no initial velocity moving back and forth. I have a damping constant, and I have my mass and my spring constant, and then I'm going to shove the object at time pi, so a is equal to pi in this case, and I'm shoving it with a force of 2 units, whatever those are. That's what this is describing, if you think about it as a physical system. Okay, Laplace transform. So here we go. You can do this as well as I can. S squared, capital X of S, minus 0s minus 0, plus 2s, capital X of S, plus 2, capital X of S. That's my left-hand side. I'm doing this for a while. We should be good at this now. Right-hand side, if a is equal to pi, this is e to the negative pi times s. That's my right-hand side. New function that I'm talking about today. So there's my Laplace transform. Okay, that's step 1. Step 2, got to get capital X of S by itself on one side. So capital X of s is e to the negative pi s over s squared plus 2s plus 2. We lost the 2. We did. We lost the 2 on the right-hand side. Sorry about that. We lost the 2 on the right-hand side. There's the 2 on the right-hand side. There's the 2 in the denominator. Thank you. Sorry about that. My fault. All right. So the bottom does not factor. Sorry, that's sad. Can't use partial fractions. Need to complete the square. So we're gonna have to complete the square in the denominator. Don't make faces at me, I can see them virtually. Go ahead and complete the square in the denominator. Do that, see what you come up with. So we still have a 2 e to the negative pi s over s plus 1 quantity squared plus 1. Okay, we've got 2 things going on at this point, and I'm going to rewrite this and we're going to go up over here. 2 things are going on at this point. First is the homework question that Daniel asked. So we've got an e to the negative pi s that's being multiplied out in front. That's the first thing. And then my function inside is 2 over s plus 1 squared plus 1. So the second thing that we have going on is an s plus 1 inside of here instead of an s inside of here. 2 different things are happening at this point in time. Let's deal with the inside part first. So this is my capital F of s, we'll call it that, 2 over s plus 1 squared plus 1. What's my little f of t then? Front of your book, what happens when you have an s plus 1 instead of just an s? This is a sign, but I've got an s plus 1. So, front of your book, I need, what do I need? I need the second column, 1, 2, 3, 4, 5, 6, 7, 8th one down. Second column, 8th one down. Second column, 8th one down. K is equal to 1 and A is equal to negative 1. So this is going to be 2 e to the negative t sine of t. 2 e to the negative t sine of t. Okay, 8th one down, s plus 1. If you want to think about, again, A is 1, that's backwards. K is 1. And A is negative 1. Okay, now we have this e to the negative pi s out in front. Ooh, did we talk about this Wednesday, Tuesday, and Wednesday last week? This is when you have a unit step function. So what I need is u of t minus pi little f of t minus pi. That's how we deal with these e's out in front. U of t minus pi, little f of t minus pi. So my final answer, little x of t, is u of t minus pi times 2e to the negative t minus pi sine of t minus pi. Daniel, this is the homework question you were asking. That's how we deal with the e's out in front. So you got to keep in mind there's a couple of different things going on here. Dealing with the e's out in front is the last part. So this is my function here. This makes sense if you think about it, right? Because when I have this u, this unit step function, that means that nothing happens until t equals pi, and then my motion proceeds according to this function over here. That makes sense because there's no initial velocity. So the object is not moving until I give it a shove. And then when I give it a shove at pi, the object moves according to this right-hand side function. So it makes sense with the way that I described the motion of the object. All right, questions on